Alright, so what is a critical chain? How does it differ than a critical path? Well, critical chain is defined as the method to plan, manage, and execute a project successfully in all time. It eliminates uncertainty within projects when one goes to schedule how long tasks are going to take within the project schedule. Then a critical path, student syndrome, Parkinson's law, and multitasking exists. Everybody knows what student syndrome is. We're all students. We wait till the last second to start a project. Parkinson's law, there's no reward for finishing early, so why do it? Multitasking is working on multiple tasks at once. It's been found that this double leads time. Within the critical chain, unlike the critical path, buffers are created throughout the project to help with these safeties that are taken out of specific tasks. We have the project buffer, as seen in this figure, that is put at the very end of the project. We also have feeding buffers, which are usually put at bottlenecks, but it's when non-critical tasks enter into the critical chain or critical path. And then we also have resource buffers, which are basically put in place so that resources are always available when needed on the critical path. Okay, the step-by-step recipe we developed based on the critical chain method. It's taken after the theory of constraints. So the first step will be identify the system constraint. Well, in project management, time is the constraint. Step 2, exploit the systems constraint. We're going to utilize buffers that we talked about on the previous slide to minimize lost time. Once again, these are the feeding buffers, project buffers, and resource buffers. Step 3 is to subordinate everything else to the above decisions. We're going to use resources within the resource buffers to focus all attention on completing the critical paths before the non-critical paths. So that means stop everything you're doing to finish the critical path tasks. Step 4 is to alleviate the system's constraints. Some examples of this is reducing the number of dependent tasks, reducing the time to perform these tasks, or reduce common resource tasks altogether. Step 5 would be go back to step 1 if the constraint is broken. It is critical not to let new non-critical chain tasks subordinate the new critical chain tasks. This goes back to resource buffers. Alright, we're learning about two main measurements within the book, critical chain. The first one is weight, which is only in the cost world, and the second one is strength, which is only in the throughput world. Weight is basically saying that any local improvement to one area of an organization will improve the entire area, the entire organization, or improving one task will improve the whole project. And the strength, which is in the throughput world, basically just says that's not the case, and most local improvements will not improve the entire organization, and that the entire organization is based on a weakest chain. This is the analogy they use in the book, where there's a weakest link. And basically the only way you can improve the entire organization is to improve this weakest link. The measurement is increased throughput, which could be, in this analogy, the links in a chain. And also focusing on planned tasks and completing each one before moving on to the next one is what this measurement asks for.
Critical chain has become an integral part of the project management environment. As such, there are now many software packages available that bill themselves as CCPM programs. These are wide-ranging in size and scope, and one such example is the Item Tracker that you see here. And this is just the basic GUI interface of the program, which shows the project timeline with the feeder buffers built in as per the critical chain process. On this slide, we have all the available critical chain software options. As I said before, this has Item Tracker, which is listed at $79 per application. And then the bigger one, which I will now talk about, is Aurora CCPM, and that's by Stokler and Hinkie, and that is actually used by such customers as Boeing and NASA for such programs as Dreamliner 787 and current space initiatives. There are other sources here, such as CC Pulse, which is an open source application in that it can be openly modified and added to at the user's will. And further adding to that, you can see that most of these rely on Microsoft Project because they are add-on programs to that application. And most of these do run on Windows. Critical Chain's core concept centers on a single project management environment. In this particular example, Critical Chain is defined as the longest sequence of tasks that are consumed throughout the entire project timeline. However, at the very end of the book Critical Chain, it is seen that CCPM management works equally well for multiple projects. And in this, the critical chain actually changes a little bit, as it becomes a restricting factor that is actually a common resource used for each individual chain. And this is an example that was taken directly from the Critical Chain book. And here you have several different processes that are independent of one another, but they all rely on the same resource, that being resource X, which is represented by the box with the X in it. As you can see, each draws on the resource, and thus the resource becomes limited. It is this limited resource that thus delays all these projects depending on when it is utilized per each one. So this is the critical chain, resource X, as you can see by the dotted line. In order to counter this, it is necessary to introduce feeder buffers before each step X in each individual process. This is where this differs from the single project management environment. By doing so, you allow for the appropriate delay to be factored in, thus reducing the overall delay. And of course, and then adding on to this, you also make sure to keep the feeder buffer in place for the final assembly, if all the projects happen to come together at the end, as you can see in this example. Critical chain is not without its weaknesses. CCPM does not account for known variables, for one thing, that being processes that are known in time and definition and quantity that can also be eliminated as factors in the CCPM process. Another problem is that the CCPM process creates long buffer durations, that being the feeder delays for this critical chain event in the process. This could be hard to justify for management and thus make the project unattainable, so this is indeed a huge hurdle. Further, CCPM does not address quality issues. It is generally assumed in the text that quality and time are interchangeable in a linear fashion. However, this is never true. So thus, it never touches on the fact that quality can and might, or will, suffer issues if a project is rushed along using the critical chain process. This is something that needs to be addressed, because quality issues are huge in the project environment. Further building upon this, it can be seen that CCPM is a very broad scope topic, and it can be used as guidelines for a key process in any project environment. Thus, using the topics discussed in the operations engineering class, it can be seen that these two work hand in hand together. Essentially, the class topics act as the basic building blocks for which the students learn basic concepts and ideas. CCPM is thus introduced, which brings these topics together. It basically can form the framework where all these subtopics are tied together and then thus strengthened. So basically, critical chain and the class material go hand in hand in a supplementary fashion. This is also true for VinSim and all the case studies. Any aspect of the operations class can and is affected by CCPM management.
Critical Chain Project Management, also known as CCPM, is the application of theory of constraints in the field of project management. We use such constraints in order to mitigate risks along each task. Several safety measures include implementing such things as buffers like project buffers, resource, and feeding buffers. Buffer length is defined from the taskings themselves. After estimates are provided for each task is reduced as a rule of thumb by 50%. And the total of that time shaved off is then added together and placed at the end of the schedule to be incorporated as the project buffer. This is the best way to reduce human behavior for waiting till the last minute. The critical chain buffers are split into three. Like I said earlier, there's project buffer, feeding buffer, resource buffer. On the screen you'll see several pictures that show the buffer either in between tasks or at the end of the tasks. Project buffer is a catch-all buffer. This buffer is posted at the end of the project, and its sole responsibility is to mitigate all risk across the entire project. The buffer allows for a project to be set for a specific date beyond the estimated completion date. This will allow for any company to use this buffer time to incorporate and integrate all of its project's designs. The feeding buffer, a buffer that presents at a task level. It helps to incorporate a buffer within the chain to allow for longer time and efforts not accounted for each particular task. For example, an engineer might take longer to design than a machinist to machine, and thus their buffers should work together to maintain the project schedule. The resource buffer is a safety net of estimated time on arrival. It particularly deals with material being ordered, or that kind of resource that you need to have time-based. These resources are usually particular to the material to account time that it takes to be purchased, and is particularly a great buffer to have with long lead items. Last but not least, there are two mistakes that can be made in dealing with identifying risks in critical chain management. It's no action if action is actually required, and acting upon them if they don't really matter. In any of these cases, allocation of resources is always our main concern.
Hello, I am Brittany Jones. Our case study discusses the issues inside the Oxford Medical Center. The center would frequently fail to meet the 4-hour turnaround target time in the accident and emergency department and regularly exceed the 12-hour trolley waits before being admitted to the acute hospitals. These two events are dependent upon one another, and since there is a natural fluctuation in their performance, this is referred to as a wandering bottleneck. The team approached the problem as a two-pronged solution. First was the dynamic buffer management, and second was treating the discharge practice as a complex multi-project environment using the Jonah discharge planning tool. TOC tells us to implement a buffer before the bottleneck in order to see if the bottleneck is always working at its maximum capacity. Using dynamic buffer management, the buffer has 3 parts, also known as zones. The zones are indicated by the colors, green, amber, and red, and the team would deploy different activities according to how far the buffer has been used up to make sure that you meet the deadline. As a result of the study, it was calculated that the level of wasted capacity in 1 year is equivalent to approximately half the capacity needed to eliminate waiting lists. This means within 2 years, the whole Oxford health system can make waiting lists a thing of the past without any extra resources. It will need the funding of the consumables required to deal with this increase in productivity. Yes, cost is involved at times, but operations engineering, critical chain, as well as the team at Oxford Medical Center emphasize that it's not always about putting more money or adding capacity, but it's about understanding the current procedures, internal policies, and most importantly, your staff.